Okay, guys, welcome back. Today, we're going to go through actually two different topics. We're going to go through 1.7 periodic trends as well as 1.8 valence electrons and ionic compounds. This should finish up Unit 1 for us. So after this, we're going to be moving on to something else. So what we're going to be doing is, one, going over the trends. What exactly do we mean by ionization energy, atomic radii, electron affinity, electronegativity, and then we're going to look at how the periodic table can help us figure out how many valence electrons there are, what type of chemical bonds are going to be forming if two elements on the periodic table come together and get close together, and then that's it for this video. And then we'll be finishing up Unit 1. Periodic trends. Here we have a periodic table. You can kind of remember that the periodic table is kind of set up in blocks, right? This is kind of the S block, P block, D block. Once the P block is full, we kind of bring back and start filling back more of the S block. Different elements are going to have different properties based on how many electrons are in their valence shell. Valence shells is how the atom can interact with the rest of the world. The valence outside electrons are going to be what are going to be shared or what are going to be lost or gained. All of that will help determine the properties of a certain element. So it makes sense that the periodic table is set up this way. All of everything in group 17 is going to have the same number of valence electrons, so they're all going to act the same way. Additionally, the further down you go on the periodic table, the larger the element is going to be, the more protons it's going to have. So that means it's going to have a stronger nuclear charge, and these are going to also affect the properties of the element as well. When you have a table like this, you can start to see certain trends. So first off, let's talk about just radius, how large an atom actually is. And what we see is that the elements over here on the top right-hand side, like fluorine, are going to be much smaller in size than the ones over here. The gray section down here is where we don't have enough information to actually tell you how large these atoms are. But you can kind of guess which one's going to be larger, francium or Rutherfordium. Okay, these guys are pretty close together. They should be similar in size, but you would imagine that francium is going to be larger because as you move this way on the periodic table, they're getting larger. So you can kind of assume that francium is going to be larger than radium or Rutherfordium. Even though we don't know that to be true, we can infer that to be true because of the periodic nature of the elements. So why exactly is it this way? Why is it that whenever we move down the periodic table, they seem to be getting larger, and whenever we're moving from right to left, they seem to be getting larger? What is the reasoning behind it? So the first reason is that as you're moving down the periodic table, you're gaining more electron shells. You're gaining more and more electrons, so the energy levels are getting larger and larger and larger. For example, hydrogen here has a single 1s orbital. For lithium, it has a 1s and a 2s, so it's going to be even larger. Sodium, 1s, 2s, 3s, and so on and so forth. So it makes sense that as you're moving down the periodic table, they're getting larger because they're having more electron shells. But why is it that whenever you're moving from sodium down to chlorine, we're gaining electrons, but they're getting smaller and smaller and smaller? Why is that the case? Well, the reason why is because they have more protons. Fluorine is going to have more protons than sodium. That larger effective nuclear charge is going to pull the electrons closer together. We're leaving the electrons at the same distance, but we're increasing the charge. So if you remember back to Coulomb's law, the two things that you need to worry about are charge and the distance of the charges. So in this case, the distance is going to stay the same. They're going to stay that, but stay the same distance away, approximate distance away. But now the protons are going to have more of an attraction because they're going to be stronger. So that's going to force that shell closer inward. Larger attraction happens at a smaller distance. So that's the reason why you have this particular trend for the radius. Remember that as you move down, they're getting larger because you're getting more electron shells. And as you're moving more towards the right, it's going to get smaller because you have more protons. More protons means more of an attraction. It's pulling those electrons closer. The next thing we're going to talk about is electronegativity. How much do these guys attract electrons? First off, let me talk about exactly what electronegativity is. It's what is the ability of the atom to attract an electron to it. So why is it that fluorine over here is going to have a much greater electronegativity than lithium? So it's the same reasoning as before. For fluorine, you're going to have the same distance, but you're going to have a much larger nuclear charge, a much bigger magnet in the nucleus because you have a whole bunch more protons. And the distance between them is going to be very, very small. So that means that it's going to attract electrons, be more attractive to electrons than something that's a little bit further away. So for chlorine, for example, chlorine, the valence electron shell is going to be further out. And since it's further out, that means it's going to be less attractive because that distance is further. Remember Coulomb's law, the charge and the distance are what matters. So that kind of explains as you're going down, you're having more shells, the distance is getting further, so you're going to have a smaller attractive force. So what about when you're moving this way, when you're moving from right to left here? Why is it that we're getting less attractive as we're moving this way? What's the difference between fluorine and lithium? They're still the second energy level, but lithium has a lot less protons. So that means that the magnet in the center is less, is not as strong, and therefore it's not going to be pulling, it's not going to be as attractive to the electrons as fluorine. Fluorine has a lot more protons. 1, 2, 3, 4, 5, 6 protons to be exact. So those are the reasons for electronegativity. I'm going to let you guys know most of these are going to be that Coulomb's law example, where it's going to be the charge and the distance of the electrons and proton. Same reason why. The first reason is electron shells. The more electron shells you have, the further away those electrons are. And then for electronegativity part 2, you have more protons as you move to the right of the periodic table, and more protons means that you're going to have more of an attractive force. Ionization energy. So ionization energy is a little bit different. This is where you need to start thinking about suborbitals and things of that nature. Ionization energy is how much energy is going to be required if you pull an electron out of it. How much energy does it take to steal an electron? I kind of think of it in this way, about how much energy is it going to be to steal a pin from a person. Now, my students know I have pins literally all over my room. They're everywhere. It's very, very easy to steal a pin from me because they're everywhere, especially like those expo markers. I have expo markers all over my room. So I would have a very low ionization energy in terms of pin because it's very easy to steal. Okay, so when you're going through and looking at ionization energy, what's going to be easy to steal from? What's going to be hard to steal from? Group 1 guys are going to be pretty easy to steal from because they have a single electron and their valence shell. That single electron is far away from the nucleus, and it has a smaller number of protons than other elements in their row. So that means that it's going to be harder for them, for that nucleus, to attract that one lone proton out on the end. Group 1, these guys are going to have a very low ionization energy, and it's going to start being harder and harder to steal as you move this way. So we're going to have increased ionization energy moving from left to right. So that makes sense. And then what about going from top down? Let's take fluorine and chlorine as an example. For fluorine, it's going to be a very large ionization energy, and as you move down, you're getting less and less of an ionization energy. And that is the same reason as before. As the valence electrons are moving further away from the nucleus, they're going to be easier and easier to steal for the exact same reasons as the electronegativity. It's going to be nuclear charge moving across this way and distance of valence electrons from the nucleus going up and down. So exactly as I said before, ionization energy, they're easier to remove when you're going down because you have more of a more electron shells further away, less attraction, easier to remove. And again, as before, more protons means that the electrons are the same distance away from the shell. It's going to be harder to remove if there's more protons because there's going to be more of an attractive force going on. All right. So this is going to be one way that that you're going to be seeing ionization energy. One thing that is going to be true is that there's not just one ionization energy. So the first ionization energy is what you see here. So I switched over to this interactive periodic table. So this is what you see for the first ionization energy. But if I switch over to the second ionization energy, what do we see? Well, we kind of see everything got shifted over. The ones that are the valence electrons for the noble gases are extremely hard to remove because they're happy they have that full octet. But whenever we switch them over, now group 1 is now the hardest to remove from because these guys now have the octet. If we've already removed one electron, the second electron that we take is the energy to remove that second electron is going to change because group 1 now has a full octet. Group 2 has a single electron, and it's going to be very easy to steal from them now. And then and group 13, 14, 15, 16, all of these have kind of shifted over. And if we switch over to the third now we see that it shifted over just another one. So the entire thing has shifted over again. What if we go to the fourth, shift it over once more, and so on and so forth. One thing that you can do is if we look at a table like this, where we see an element and it has a first ionization energy, and then a second, third, fourth, so on and so forth. What you can do is look to see where the jump is. So the first ionization energy is pretty low, and then it jumps up, almost tenfold. We can assume that this guy is going to be a group 1 element because the first ionization energy is pretty low, and then the second ionization energy jumps up and is super, super high. So you can assume that if the first ionization energy is low and then it jumps, it's going to be a group 1. This guy, it's pretty low, jumps up. So the third ionization energy is where you see a large jump. So when you think about it, the first 2 electrons are pretty easy to steal. This means that this guy is probably a group 2. For this, the first 3 are pretty easy to steal, and then the fourth one is hard to steal. That means that this has 3 valence electrons, and then the fourth one is that octet, the 8th in the octet. So this is probably a group 3, and so on and so on and so forth. This is, if I kind of move this out of the way, you can see that it's true. Sodium, magnesium, aluminum, so on and so forth. Group 1, 2, 3, 4, 5, etc. So that's ionization energy. Those are the rules for ionization energy. The next thing we can think about is electron affinity. So electron affinity, this is how much energy is released whenever you shove an electron into it. Now, what do you mean energy being released? Well, one drawing that I know my students know that I absolutely love is this guy. If I draw this graph, and this is potential energy. This is potential energy on the y-axis, and this is going to be distance on the x-axis. Graph is typically about 2 atoms being close together, and what is their potential energy? And what you see is that there's going to be a certain point where they're very, very stable. It's a very low potential energy point. And this is going to be your bond length. So as the electrons or as the atom moves close together, they they're going to be attracted to one another, and then if they get too close, they're going to be repelling each other. And this is going to be the kind of that sweet spot where there's a distance between two atoms that is a certain distance, and this is going to be your bond length. This is your bond length. So this is going to be a very similar idea here, where you have a certain number of electrons that will give you a very stable setting. But what does that mean? What gives you an actual stable setting? Well, as we said before with electron configuration, a full energy shell is going to give you a stable scenario. So a full 1s orbital, great. That's going to give us one. A half full one is going to give you stability. So for example, if I looked at a p orbital, let's say this is 2p, and I had one electron. If I added another electron, now I have some stability. So this leads to a little bit more stability than a situation where I have just where it's not half full. The most stable situation is where the 2p orbitals are completely full. That's going to lead to the most stability. When we're talking about electron affinity, we're talking about how much energy is released whenever you're adding an electron, whenever you're making a negative anion. So this is kind of that same idea of, remember, if you're moving down on an energy diagram, you are releasing energy. It's the negative energy. Negative energy means that you're releasing it. And remember, lower energy is more stable. What does this mean about periodic trends? Let's go back to the periodic table. Let's look at electron affinity. So if you look at electron affinity, initially you think, holy crap, this has no pattern in it whatsoever. But if you look, you can start seeing some patterns. Where are the stable guys? At the end of the S block, very, very stable. At the end of the D block, very, very stable. At the end of the P block, very, very stable. And then if you look halfway, nitrogen here is very stable because nitrogen is very stable because nitrogen has 2p, and let me draw some orbitals. It has 1, 2, 3. Very stable. It's very, very stable. Carbon. So if this is carbon, and I were to add another electron, that would mean it's going from something that's high potential energy down to much lower potential energy. So we're releasing a lot of energy. So carbon has a very high electron affinity because we're moving from a very unstable setting to where it's not half full to a more stable setting where it is half full. Same way with fluorine to neon. We're moving here. We're in a situation where we just need one more electron. For fluorine, we're going to be in a situation like this, where we have 5 electrons in the 2p orbital, 2p5. We're at some energy level. And then if we add another electron, we're going to drop to a very stable energy level, which means we're going to be releasing lots of energy. So that is electron affinity. Think about, if I added one more electron, how much more stable would it be? And in terms of stability, think half full or completely full shells. The other thing you need to think about is, what is the valence electrons? In other words, if you were to ionize this thing, if you were going to turn it into an ion, what would its charge actually be? So everything in group 1, where you have 1 valence electron, and if you were to ionize these guys, they would turn into +1 ions because you were losing that 1 extra electron, and now it's at 8 octet. Losing 1 electron leads to a +1 charge. Group 2 is going to be losing 2 electrons, being a +2 charge. Boron and aluminum, losing 3 electrons, becoming a +3 charge. So carbon and silicon are going to either gain or lose 4 to become either a plus or a -4. Everything in 15 is going to, now we're going to flip to the other side. We're now going to be gaining electrons. So we're going to be gaining electrons with group 15, gaining 1, 2, 3 to be a -3. We're going to be gaining 2, -2 ions. Gaining 1, -1 ion. And then 18, these guys are already at an octet, so these guys don't move at all. So that's it for today. Hope everyone is staying safe out there. We're going to be heading back into school soon, at least for my students. For all the other people out there, hopefully you guys are staying safe. I don't know if these videos are going to become more frequent because I'm going to be having an actual schedule, or less frequent because I have to deal with a lot of bureaucratic meetings and things like that. Hopefully it'll be more, not less. See you guys later. Have a good one.